Okay, we are at section 1410, standing waves in air columns. This is very important because this is what we're going to be doing uh, Tuesday. We'll be doing this Tuesday, uh, air column resonance, and we're going to be generating standing waves in tubes. Let's share the PowerPoint and go on with the next slide. Okay, we have a pipe open at both ends. Now, let me just tell you, it's hard to uh, produce a resonance. It can be done. I mean, they do it in pipe organs, but just like blowing through it or with a tuning fork, it's hard to set up a uh, standing wave in a air column that's open at both ends. But just take a look at this, and obviously at the ends of the open pipe, there's not going to be a node because the air molecules are free to vibrate at either end. So it's always going to have an antinode. There's always going to be an antinode at the ends of the open pipe. So if you have a pipe open at both ends, you have the first harmonic. What is that? If you just follow one of the lines, you're going from one side to the opposite side. So that's only a half of a wavelength. So the fundamental lambda 1 is equal to 2L. It's equal to twice the length of the pipe. So the fundamental is the velocity of sound over lambda 1, which is the velocity over 2L. We have it here. Length is equal to 2 over, it's 2 quarter waves. From antinode to node is a quarter wave. Node to antinode is a quarter wave. And so there's 2 of them. So you have 2 quarter waves. So it ends up being lambda 1 over 2. The length is lambda 1 over 2. It's a half of a wavelength. So the frequency is equal to the velocity divided by lambda 1, which is V over 2L. Now, the second harmonic, you have it's open at both ends. Now, if you just follow one of these lines, you go from the antinode starting at the bottom, you go to the antinode at the top, and you go to the antinode back at the bottom. So that is a full wavelength. That is a full wavelength. So lambda 2 is equal to L. But how many quarter waves? There's 1, 2, 3, 4 quarter waves. So F2 is equal to V over L is equal to 2 F1. The third harmonic, lambda 3 is equal to 2/3 L. So you have F of 3 is equal to 3/2 V over L, which that's equal to 3 F1. It's 3 times the fundamental. So F, for a general F of N is equal to F of N is equal to N times V over 2L equals N times F1. So you're going to get all the harmonics. N equals 1, 2, and 3. You're going to get all their harmonics. Not the same with the closed pipe. And that's where we go here. We have a pipe closed at one end. Now, whenever it's closed, the air molecules can't move there. So it's going to have a node. There's always going to be a node. There's going to be an antinode at the other end. So they're always going to have a node at the end and an antinode at the open end. So you have the first harmonic. Lambda is equal to 4L. In other words, L is a quarter wave. From a node to an antinode is a quarter wave. So lambda 1 is equal to 4 times the length of the tube, since it's only a quarter wave. So F1 is equal to V over lambda 1 equals V over 4L. Now, for the third harmonic, lambda 3 is equal to 4/3 L. So that's equal to 3V over 4L equals to 3F1. Now, notice there's no second harmonic. There's not going to be a fourth harmonic. In fact, there's not going to be any even harmonics. It's all going to be odd harmonics. The first, the third, the fifth, the seventh, and so forth. So L equals lambda 1 over 4 equals lambda 1 equals 4L. L equals 3, 3/4 lambda 3. So lambda 3 equals 4L, 4/3 L. So the fundamentals, I mean the harmonics, which is n, f of n is equal to n times v over 4L equals n f of 1. So n in this case is 1, 3, 5, 7, 9, and so forth. It's only the odd harmonics. Okay, I'm going to continue on with beats, and I've even got a little, I think I've got a demonstration. Now, beats are when you have two frequencies that are very close to one another, so that you have combinations of destructive and constructive interference. You can experience this sometimes coming up to a stoplight, and if your engine revolutions are very close to the engine revolutions of your neighbor pulled at the stoplight, you'll hear this vroom, vroom, vroom. You'll hear this beating between the two engines that are at very similar RPMs. But we can do it with tuning forks. I think I have a little demonstration video of beats. You get, basically it's just the frequency of one minus the frequency of the other. So let's just say we have 1,000, a tuning fork at 1,000, and we have a tuning fork at 1,003. That we play them together, they're gonna, what would be the beat frequency? It would be 3 hertz. 1,003 minus 1,000 would be a 3 hertz beat. It would produce a 3 hertz beat. So the beat frequency is equal to the absolute value of F2 minus F1. And that's where I'm going to stop. We're going to do this quality of sound and the ear next.